Hello everyone, this is Mrs. Jackson. This is Chapter 1, Section 3, Part 1. In this section, we're going to be talking about something called piecewise functions. A piecewise function is a function that has different rules, so in other words, different equations, for different sections of the function. So if you look at the graph below, you can see it's kind of broken up into different pieces, hence the name piecewise functions. So by the textbook definition, the way we always describe different intervals of a function is with the domain. So I'm going to say different rules for different sections of domain. Piecewise functions are actually used more in real-world applications than other functions, one of them being volume pricing. So in other words, the higher the volume that you buy of a particular thing, you tend to get a lower unit price for that. And that would be described as a piecewise function. So in this graph here, we've got three different pieces. We've got segment 1 in blue, segment 2 in red, and segment 3 in green. We're going to describe each of these pieces, if you will, with domain, and we're going to describe them as what type of functions they are, and we're going to describe them with a function, in other words, an equation. So let's start with segment 1. If you recall from a previous section of notes, segment 1 is a flat horizontal piece, and we call that a constant function. So I'm going to just write what type of function it is, constant function. And you could see that the output of the constant function is consistently a 7. So in terms of the equation, we would write f of x equals 7, or you could just always use just a 2 variable as well, y equals 7. However, that's restricted to a certain section of domain. As in the case of all intervals, we describe them with the x values, the domain. So our segment 1 is beginning at a minimum of -5, and it's ending at -2. Do note again that these points are filled in. That means that segment 1 is equal to 7 when x equals -5. It's equal to 7 when x equals -2. So when we describe that domain, we're going to use or equal to. So I'll put this first, maybe I'll shoehorn this in a little bit in here with an inequality. So x is less than or equal to -2 as our maximum, and greater than or equal to -5 as our minimum. Maybe right over here, just put it in interval notation just to reinforce that. Segment 2 here is in red. That's a linear function. So I'm going to write that down here. It's a linear function whose y-intercept equals +5 and whose slope is negative, and the slope is going down 1 over run. So the rise is -1 and the run is 1. Remember, the run is always positive, so we're just going to say the slope is -1. We have to decide what this point is and where this point is located. When these pieces touch each other, like here at this point, -2, 7, that's put in blue, and I'm recognizing that in blue because I want that point to be part of segment 1, but it is not going to be a part of segment 2. So that point, we have to decide, is it in this segment or that segment? I tried to show that with color. So if we look at the domain here for segment 2, the domain x is less than or equal to 3, +3 here. And it is a filled in circle, so I'm going to say or equal to. But I'm only going to use greater than -2 as the minimum. So I would show that with parentheses. At x equals -2, we're not going to touch that because it's over in segment 1. But we can touch the +3, so I'm going to put that with brackets. Okay, so to finish up then, we're going to write its equation, and as we know, linear functions is y equals mx plus b, and the y-intercept is b. So we've got f of x equals negative 1x, or I'm just going to put negative x plus 5, or you can just as easily write that in two-variable form. All right, last piece is over here in green, which is also linear, as you can see. One end point of it is an open circle, and the other is a closed circle. So we've got an equation that is also linear function, and we can't readily read its y-intercept off the graph, so we're going to have to figure out what that is. Y equals mx plus b, and we know our slope is positive, and we know it's a positive 2. We can read that right off the graph. We're rising 2 and running 1. So we've got a slope of 2. So I'm going to put that in here, 2x plus b, and I'm going to have to solve for b. And I'm going to do that by substituting in any point that's on that little piece there. So whatever point you want to choose, I'll go ahead and choose this first end point here, x equals 4, y equals 5, so I'll pop that in there. So y equals 5 when x equals 4, and I can solve for b. That's going to turn into 5 minus 8, so b is going to be negative 3. So our function then is f of x equals 2x minus 3, and that's restricted to a certain section of domain. So that is x is less than or equal to 6 on the maximum. I'll just point that out here with my highlighter. And then x is greater than positive 4. And it's not or equal to positive 4 because of that open circle. So I'm going to show a parentheses in my interval notation at 4, not equal to 4, and it's going up to 6, and all the numbers in between. I can touch 6, so that's going to be a bracket. Okay, so the last thing we need to do for a piecewise function is bring it all together. We want to describe all these pieces together as one function, and since there's more than one of them, we would call that a set, just like a list of numbers would be a set. And as always in math, we describe a set with braces. So we are going to describe this function all together as f of x equals the set of, and I'm going to make big braces here, and I'm going to describe each of the three pieces along with the domain that describes it. So I've got f of x equals 7, and that is true for the values of x that are greater than or equal to negative 5 and less than or equal to negative 2. Likewise, f of x equals negative x plus 5, and that's true for all the values of domain such that x is greater than negative 2 and less than or equal to 3. And finally, the last piece is f of x equals 2x minus 3, and that's true for all values of x such that x is greater than 4 and less than or equal to 6. And so that is piecewise functions. Bring together a bunch of different rules and equations into one single function. In class, we're going to be applying this to some word problems, but this is a quick review of how to describe a piecewise function. Hope this helps.